Good morning, everyone. I welcome you all in the first online refresher course in the chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor Director, UGC HRDC, and Dr. Dilip Wasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, Gujarat University.
Good day, friends. I welcome you all to this UGC-sponsored fifth online refresher course in chemistry that is organized by UGC MMTTC Gujarat University. I, Dr. Bhupesh Bhatt, Assistant Professor, Sardar Patel University. Thanks UGC MMTTC Gujarat University for giving me opportunity to connect with you. I also like to thank Director of UGC MMTTC Gujarat University, Dr. Jagdish Joshi sir, and coordinator of this program, and my dear friend Dr. Dilip Vasal sir, for inviting me to discuss this very interesting topic, Mossbauer spectroscopy. UGC MMTTC ranked 15th in India, and I have also attended my orientation course and my two refresher course over here, that is at Gujarat University, and my experience is wonderful. It is excellent over here. My experience is excellent over here. So for that, I would like to congratulate Dr. Jagdish Joshi sir for efficiently executing these duties of director for so many years. I also like to thank Dr. Dilip Vasawa sir, who is a very good researcher and good teacher, and my good dear friend. So let's start with our today's topic, that is Mossbauer spectroscopy. So my first question is, what do you mean by spectroscopy? So it is very simple. Spectroscopy is the interaction between any electromagnetic radiation and any material or matter or any sample. So when material or sample absorb the electromagnetic radiation, some changes are going to be occur. Whether these changes are in the form of a change in the rotational energy level or vibrational energy level or electronic energy level or any other kind of changes. Okay. So we can see the electromagnetic spectrum over here, in which over here, that is at low energy side, we have this radio waves. Then we have microwave, IR, U visible, X-rays, and gamma rays. Radio waves and microwaves are considered to be least energy electromagnetic radiation, and the spectroscopy which are connected to these two radiations are nuclear magnetic resonance, that is NMR, to this radio waves, and ESR, that is electron spin resonance, to this microwave radiation. Then we have IR. We all know about the IR. We also know about the U visible. Many techniques are related to this X-rays, and then high energy electromagnetic radiation, that is gamma radiation, which is our today's topic of interest, that is Mossbauer spectroscopy, which is related to this gamma radiation. So before moving to this uh, Mossbauer spectroscopy, I would like to discuss a very basic phenomena of this beta decay process, because it is very important to understand this beta decay process. Without understanding this decay process, we cannot move toward this Mossbauer spectroscopy. So what is beta decay process? Through this beta decay process, either proton can be converted into neutron or neutron can be converted into proton by electron capture or electron emission. So based upon that, it is called as beta plus decay or beta minus decay. So we can see that carbon 14 can be converted into nitrogen 14 by conversion of one neutron into one proton. So since number of protons are changing, we will be having a new atom. But since the total number of protons and neutrons are same, we will be having the atomic mass, that is the atomic mass will remain the same, and that's why we will be now having atoms of different isotopes. different isotopes of atoms. In a similar way, over here we can see that one neutron is converted into one proton. So again, the atomic mass remain the same, but now we will have a new element or new atom. So this fundamental information will be useful, that is beta decay process, to understand this Mossbauer spectroscopy. Now, what is Mossbauer spectroscopy? This Mossbauer spectroscopy involves the nuclear transition which results from the absorption of gamma radiation. So by absorption of gamma radiation, there will be a nuclear transition. As we can see in the case of NMR, we will be having rotational energy level change. In the case of IR, we have vibrational energy level change. And in UV visible spectroscopy, we have change in the electronic energy level. Now, in any spectroscopy, the important thing is absorption of electromagnetic radiation and uh, number of peaks which are going to be observed and what is their peak position. So in this spectroscopy, this absorption of radiation, it will depends upon electron density about the nucleus. Okay, and the number of peaks are which are observed are related to the symmetry of the compound. If we take the example of NMR, we will be having absorption in the form of delta ppm, that is chemical shift value. In the IR, we have that wave number nu bar. In the case of U visible, we have that lambda max. If we take the case of example of NMR, then number of peaks are related to different kinds of proton. So in the case of Mossbauer, this number of peaks are related to symmetry of the compound. Now, why we need to study this Mossbauer spectroscopy? So basically, this is an inorganic spectroscopy, and it has application in solid state physics, metallurgy, and biochemistry. Now, what is the beauty of this spectroscopy? You can see that if we have any unknown material or we have any ores, alloys, foreign material, then and if it is having some content, this content may be down to 0.03% uh, of iron or tin or any other element which can be studied through this Mossbauer spectroscopy, then can be detected by this spectroscopy. You can see that the concentration is even 0.03% that can be studied by this spectroscopy. Also, for example, if we have Fe and it has a different oxidation state, we know that Fe has Fe plus 2 and Fe plus 3. Sn has or tin has Sn plus 2 and Sn4, Sn plus 4. So that relative percentage of different charge states of same atom can also be studied by this Mossbauer spectroscopy. And in this way, this is important spectroscopy. Now let's discuss the principle. The principle in one line we can say that it is a recoil-free or recoil-less gamma ray energy resonance absorption phenomena. So what is resonance absorption? That is when energy of source material and absorber material matches, we will be having resonating condition, and in that case absorber material is going to absorb the gamma radiation. We will try to understand this recoil-free gamma ray energy resonance absorption by taking the example of 57 Fe, and most of the work on this Mossbauer spectroscopy have been done on this 57 Fe atom element. So for example, we have 57 Fe and we know that the ground state of 57 Fe is I is equal to 1 half, and excited state of this 57 Fe is I is equal to 3 by 2. The energy difference between this ground state and first excited state is 14.4 kilo electron volt. So when this nuclei of 57 Fe comes from excited state, that is first excited state, to ground level, it will emit the energy of 14.4 kilo electron volt, which is considered to be very high magnitude of energy. So the gamma radiation which are emitted will be having energy of around 14.4 kilo electron volt. Now why I am saying the word 14.4, around 14.4 kilo electron volt, that we are going to discuss on the later part of this lecture. Now This is about the source material and it emits the gamma radiation. Now over here, so let's consider this figure. Over here we have a source material and over here we have a absorber material. That is a sample material. This is a sample material. So when nuclei come from excited state to ground state, it will emit the gamma radiation of 14.4 kilo electron volt. Now let consider this absorber material. This absorber material is having some energy level difference, and if this energy level matches with the energy of that gamma radiation which are emitted over here, it is going to absorb the gamma radiation. Okay, now over here we have two catches. The first catch is about the emitted radiation, that is gamma radiation. Now when these gamma radiations are emitted, some amount of energy is going to be recoiled. Now what is the meaning of recoil? We will take one simple example of gun. When any man shoot the bullet from the gun, uh, the thrust produced results into the movement of that gun to the opposite direction of that movement of that bullet. So some amount of energy is recoiled. Okay, so that is called as recoil energy. Now when over here, when the gamma radiations are emitted from here, some amount of energy is recoil. That is recoil energy is R over here, and R can be expressed by this P square by 2m. M is a mass and P is a momentum. So when the gamma radiation, see, we are talking about the resonating condition. Okay. So our first problem is how much amount of energy is emitted, or what is the magnitude of energy of this gamma radiation emitted from here, that we don't know because of this recoil factor. We don't know what is this R recoil factor, we don't know. Okay. So, and what is the second problem? Second problem is with this absorber material. For example, if over here we have 57 Fe as the absorber material, but this 57 Fe in the absorber material or sample material may have some different environment than the source material. For example, if we talk about generally the source material over here, we can say that the 57 Fe which we are talking about here is isolated 57 Fe and it is free from any external factors over here. But this sample material, it can be in any ore material, it can be in any alloy material, it can be in any ferromagnetic environment, it can be any cubic environment, it can be in the non-cubic environment. So based upon the electronic environment of this absorber material, the energy level difference of the ground state and excited state is going to be varied in the case of absorber material. Okay, so when these gamma radiations are emitted from here, they are going to be moved from here, from this absorber material, and these radiations are not going to be absorbed by this absorber material. Why? Because the energy level difference between over here in the excited state and ground state of source material is not going to be matched with the energy level difference between the excited state and ground state of this absorber material. So how to solve this problem? How to solve these two problems? Okay, so let again summarize this thing that we have two problems. The first problem is due to this recoil fraction, that is R. We don't know what is the magnitude of this emitted radiation. And second thing, we don't know what is the environment of 57 material over here in the case of absorber material, whether it is ferromagnetic, paramagnetic, cubic or non-cubic. So we are going to address these two problems in this Mossbauer spectroscopy to understand the principle of this spectroscopy. Okay. First of all, this R is equal to P square by 2m. So by increasing the mass, we can easily reduce this recoil fraction. And that's why to minimize this recoil energy, generally we put this 57 Fe, which is a source material. See, actually our source material is this 57 cobalt. Okay, this actually what happens, the source material is 57 cobalt, and through that beta decay process which we have discussed earlier, it is converted, that is through electron capture, it is converted into 57 Fe over here. So this I is equal to 5 by 2 is the second excited state of 57 Fe. So this process is beta decay process. So our source material is 57 cobalt, and this source material is going to produce 57 Fe, and we are interested over this region, that is ground state and first excited state. Okay, so what we do to minimize this recoil fraction, we generally put this 57 Fe in the uh, nuclei, or the in the environment of element having very high atomic mass. For example, we generally put this 57 Fe embedded in the rhodium material. Okay, so rhodium is a very high atomic mass element, and that can be served ideally as a good gamma radiation emitting agent, so that we will be having minimized recoil fraction. Now, second problem, that we don't know about the energy level difference between the absorber material. So what we can do, we can emit the gamma radiation of different energy from here. Now, how it is possible to emit the gamma radiation of different energy through the same source? So for that, let consider over here. Let understand over here the instrumentation of this Mossbauer spectroscopy. So you can see that we have this Mossbauer drive over here. This is Mossbauer drive. Over here we have a rhodium material in which 57 cobalt is embedded, which is our source of this gamma radiation. Now you can see that this reciprocating motor is attached to this Mossbauer drive, and that's why this Mossbauer drive will, what it will do, it will create movement of this source material. Okay, so through this reciprocating motor, this source material will be either moving toward the sample, or it will move away from the sample. Okay, so generally we can we say this phenomena as the Doppler shift. So we can say that our source material is Doppler shifted over here. The velocity of this uh, motor or Mossbauer drive is of the magnitude of millimeter per second. It is very less. But since there is some velocity of this source material, now the gamma radiation which are emitted will be having magnitude energy of different magnitude. Either it may have higher energy than 14.4 kilo electron volt, or it will be having less energy than 14.4 kilo electron volt. It is going to move from the collimator, and then it will move toward the sample. Now see, most of the radiations will pass to the sample material. Now which radiation are going to be passed from this sample material, for which the energy level difference between the source material and absorbed materials are not matching. Over here we have a detector. Detector is a Geiger-Müller counter which counts the gamma radiation. So when a particular gamma radiation which will be having energy matches with the energy level difference of the excited state and ground state of this sample material will absorb that radiation, and at that time, at particular velocity of this Mossbauer drive, we will be having a sharp fall in the gamma radiation count, which is counted at Geiger-Müller counter. So we will be having one peak over here, which generally represent a sharp fall in the gamma radiation count over here. So in this way, we get a peak. See, this is a count of gamma radiation, and this is counted by this Geiger-Müller counted. So in this way, we get peak or signal in the case of Mossbauer spectroscopy. So let again consider this figure. We have the source material, it will emit gamma radiation. We have absorb material, it absorbs the gamma radiation. When energy matches, we will be having a sharp fall in gamma count, which is observed over here in the form of a signal or peak. Now, in this way, we can know about the peaks observed in the case of this Mossbauer spectroscopy. Now, what is about the position of the peak? See, you can see that at this moment, for example, and for conveniency, I have shown the peak at 0 value. Okay, but this may have some positive value or it may have some negative value. So in which case we will be having a positive value, in which case we will be having a negative value, in which case we may observe more than one peak. So for that, we need to understand the factors which are going to affect this Mossbauer spectroscopy. So that is the second part of our spectroscopy. Okay. Now, what is the recoil effect? Recoil effect we can understand by this simple diagram. This is uh, this is the probability of matching the energy. In this figure, we can see that this region is the probability. See, we have source material, we have absorber material, and this is the probability. Higher the probability of matching the energy, lower will be the recoil energy. So by minimizing this recoil energy, this is recoil energy. So by minimizing this recoil energy, we can increase the probability of matching the energy of source material and the absorber material. Now, characteristic of Mossbauer nuclei. For example, over here we have discussed the 57 cobalt material. In the same way, there are many other Mossbauer nuclei which can be considered as a source material. For example, we can talk about 119 SN. We can also talk about Fe and elements like zinc, nickel that can be also serve as the ideal source material. And what are the characteristics of that Mossbauer nuclei? The energy level, the energy range of gamma radiation emitted should be 10 to 200 kilo electron volt. The half-life, obviously, it should be of the order of year. For example, in the case of 57 cobalt, the half-life is around 250 days. So same source material can be used for the longer period of time. If we take some nuclei which is having half-life of some month or some days, then on the basis of very frequent time, we need to change that source material. Half-life of excited state of absorbed nuclei should be within the limit of 10 raised to minus 6 second to 10 raised to minus 10 second, which is the range of our instrument. Conversion coefficient should be as low as possible, and absorbed nuclei should be present in higher isotopic abundance. For example, if we talk about 57 Fe, then if we compare the natural abundance of 56 Fe and 57 Fe, then the abundance of 56 Fe is 98%, but the 57 Fe, the natural abundance is 2%. So that 2% is enough to study the absorber material. Now, this spectroscopy is given by Rudolf Mossbauer. Uh, he passed away in 2011, and this Mossbauer spectroscopy is the work of his PhD. During his PhD, he has discovered this beautiful spectroscopy, and he embedded this radioactive sample in a crystal and cooling them. Their tightly held crystal position prevented them from recoiling. That is, the material is rhodium material. The energy of recoil had been absorbed by the lattice as a whole. Now, Rudolf Mossbauer, what is Lamb-Mossbauer factor? Mossbauer, Mossbauer, there's a Rudolf Mossbauer, he's the name of scientist, perform an experiment of recoilless gamma radiation absorption and emission in solids. Now, he has taken the recoilless fraction of gamma radiation which are emitted. See, our first task is to minimize that recoil energy. So he has done that thing by taking a very small fraction, that is recoilless fraction of this gamma radiation, and this recoilless fraction of gamma radiation is f is equal to exponential minus e h omega a, where omega is the angular frequency of oscillator, E is the energy, and h is a Planck constant. So during his PhD work, he has taken this recoilless fraction of gamma radiation emitted to study this Mossbauer spectroscopy. So up to here, we have talked about the basic principle of Mossbauer spectroscopy. So the basic principle is that recoilless free energy. Okay. We have two problems here that we have discussed, that is about recoil free energy, and the second problem is the environment of this absorber material. Now how this environment of this absorber material is going to affect the energy level difference of this excited state and ground state, and also how this energy level difference is related to number of peak observed over here. See, in this case, we have only one peak, but this peak can be 2, 3, or many more peaks. Okay, so how we may get different peaks and different number of peaks in the Mossbauer spectroscopy, that we are going to understand in the next part of this lecture. Okay. So now we are going to discuss which factors are going to affect the number of peaks and position of peaks in the Mossbauer spectroscopy. We all know that the unique feature of this Mossbauer spectroscopy is production of highly monochromatic electromagnetic radiation, so that it can be used for resolving minute energy perturbation. Application of this Mossbauer spectroscopy arises from its ability to detect a small variation in the energy of interaction between nucleus and extranuclear electron, which are going to affect the position and number of peaks in the Mossbauer spectroscopy. So these are the three factors, that is isomer shift, quadruple interaction, and magnetic interaction. So let's consider the isomer shift, which is the first factor. So when absorber and source nuclei, absorber nuclei is our unknown material, and source nuclei, that is 57 cobalt, which is converted into 57 Fe through beta decay process. When these two are in different environment, it does not absorb at the same frequency as original nuclei that we have already discussed. This isomer shift reflects the differences in the s electron density around the emitter and absorber nuclei. Now this s electron density is going to affect this isomer shift. Isomer shift is the position of the signal. Okay, whether we are getting this peak on the negative side or on the positive side. So that is our isomer shift. So this depends upon the s electron density. On the same time, this isomer shift also depends upon the electron density of d electron. Why? Because d electron screened the interaction between nuclei and outermost s electron. Okay, and that's why if we will have more d electron density, ultimately it going to reduce the effect of s electron density. Okay, so more the d electron density, there will be a less effect of s electron density. The electronic interaction between the nucleus and the surrounding electron can shift the nuclear energy level. So in this way, the energy level difference we will be having. Now, see, when I have talked about the energy level difference between the source material and absorber material, that energy, the magnitude of that energy level difference is of the magnitude of 10 raised to minus 8 electron volt, which is considered to be very low if we see the energy of gamma radiation, which is having magnitude of 14.4 kilo electron volt. So again, I can say you that this is very beautiful spectroscopy, because through this spectroscopy, we can measure or resolve the minute energy perturbation, and which is the magnitude of 10 raised to minus 8 electron volt. So this is a very sensitive spectroscopic technique. Now this is a very simple expression through which we can understand this isomer shift. It is equal to K SE square minus SG square. K is a universal proportional constant. SE and SG are S electron density in excited state and ground state. On the same way, over here we have RE minus RG divided by RG, and over here the RE and RG are the radius of nuclei in the excited state and the ground state. Now, when there is increase in S electron density in 57 Fe, spectrum will give a negative shift because the change in effective nuclear charge is negative, owing to Re less than Rg. What is the meaning of this thing? That when we have 57 Fe, if the electron density of S electron is increasing, that means we will be having more isomer shift toward negative side. That is, now we will be having signal on the left side of 0, as we have seen the spectrum. And in this case, the value of Rg will remain higher compared to Re value. That is, over here we can see that we will see a phenomena of nuclear expansion and nuclear compression. Means the radius of nuclei is going to be decreased or it is going to be increased in this case when it emits the gamma radiation or it absorbs the gamma radiation. On the opposite side, if we talk about this 119 SN, that is teen, we will be having a positive shift. Now, why we get positive shift? Because the overall nuclear charge owing to Re greater than Rg means the radius of nuclei in the excited state will remain higher of 119 SN when there is more S electron density compared to the ground state. Now, if we talk about this, okay. Again, consider the case of this 57 Fe. Now you know that when we have 57 Fe, as we have more S electron density, there will be shifting in the negative side, more negative side. But what will happen if we study the Fe plus 2 and Fe plus 3? So we know that in the case of Fe plus 3, the electron is removed from d orbital of Fe plus 2. Okay, so now we have a lower d electron in the case of Fe plus 3 compared to Fe plus 2. So there will be a lower screening of S electron from the nuclei, and that's why the magnitude of S electron is going to be higher in the case of Fe plus 3, and that's why we will be having even lower isomer shift value in the case of Fe plus 3 compared to Fe plus 2. So in this way, the position of signal is going to be shifted in the case of Mossbauer spectroscopy. Let's understand this thing by this simple figure that in the earlier I have shown you that this signal is observed at 0, but as there is increase in S electron density, or decrease in d electron density. Okay, so this both things are complementary to each other. In the case of these two phenomena or either of this one phenomena, we will be having a compression of nuclei, and that's why the isomer shift is negative in the case of 57 Fe. But in the case of team, that is 119 SN, the increase in S electron density or decrease in D electron density will lead to expansion in nuclei radius. And that's why we will be having a positive shift in the isomer shift. So over here, we have a negative shift in the case of 57Fe, and over here we have a positive shift. Now, if we consider again, as we have mentioned over here, the case of Fe plus 2 and Fe plus 3, in Fe plus 3 we have less d electron, and that's why the effect will be even higher. We will be having more negative isomer shift value. Likewise, in the case of Sn plus 2 and Sn plus 4, we can see that in the case of Sn plus 2, we have 2 s electron in the case of Sn plus 2. But in Sn plus 4, this s electrons are going to be removed from here. And that's why now, since we don't have any outermost s electron, the isomer shift in the case of Sn plus 4 will remain the 0. But in the case of Sn plus 2, the isomer shift is 3.7 plus 3.7. So in this way, we can judge that at which position we are going to get the signal of Mossbauer in the Mossbauer spectrum. So this is about isomer shift, which is based upon the compression and expansion of nuclei radius, and through which we can understand whether we are going to get the signal on the negative side and what will be the magnitude, or we are going to get signal on the positive side and what can be the magnitude. Apart from this isomer shift, we have one more factor, which is a quadrupole interaction or splitting. Quadrupole moment, this thing also we have studied in the case of NMR, in the case of 14N, in which the I value of 14N is 1, and that's why we will be having a quadrupole moment, and due to that we generally get broad signal for the proton attached to the nitrogen atom. Now, in the case of Mossbauer spectroscopy, the general meaning of quadrupole interaction is that when nuclei is having spin value greater than half, okay, that is either 1 3 by 2 or 2 or 5 by 2, like that, means it is not 0 or half. In that case, the s electron density or the charge is distributed spherically symmetrically, means charge distribution is equal to the on all the direction. Okay, and that's why we can say that charge distribution is spherically symmetrical when the I value is either 0 or half. But if it is greater than half, that means the charge distribution is not spherically symmetrical. So how it is going to affect the number of signal and the position of this spectrum? So in the case of an isotope with I is equal to 3 by 2 excited state, such as 57Fe or 119SN, the 3 by 2 to 1 by 2 transition are splitted into two substrate, that is plus minus half and plus minus 3 by 2. So ground state and excited states are further splitted into two different energy level. So this appear as two specific peaks in the spectrum, and sometimes they are also called as the doublet. So we can see over here the example. You can see that when we have this quadruple shift, that is I value is greater than half, that is it can be 1 or 3 by 2, the excited state is further splitted into two different signal. So now two transitions are possible. In the earlier case, we have only one transition, and that's why we get only one peak. But over here, we have two transition possible, and that's why you can see that through quadrupole splitting, we will be now having two different signal for this particular nuclei. Maybe this nuclei is 57Fe, but it will be having a different environment. See, I have already told you that if we consider 57Fe, then this 57Fe may be the environment of this 57Fe may be in the stainless steel, or it can be in any ore or alloy. It can be have some ferromagnetic environment. So based upon this environment, these factors governs on that. That is isomership, quadrupole splitting, Zeeman effect. Okay, and based upon that effect, we will be having different kind of signal and different number of signal. Okay, so we can judge what is the environment of the same nuclei by using this spectroscopy based upon the position and number of signal through this Mossbauer spectroscopy. Now the third factor is magnetic interaction or nuclear Zeeman effect. So the magnetic field at the nucleus produced by the surrounding can interact with the nuclear magnetic moment. The interaction destroy the degeneracy of nuclear level. So in the earlier case, we have seen that the energy levels are degenerate, means the energy, the peaks are not splitted further. But if the 57 Fe is in the ferromagnetic environment, the magnetic moment of that environment is going to affect the nuclear magnetic moment of 57 Fe, and that's why the degeneracy of energy levels is going to be destroyed. Now, number of level depends upon magnetic quantum number of nuclei, that is 2i plus 1 levels. Now let consider a simple case that we have ground state I is equal to 1 by 2, I is equal to 3 by 2. Now you can see that due to magnetic moment, the degeneracy of this ground state and excited state is destroyed over here. You can see that ground state is splitted into two different peaks, and excited state is splitted into uh, four different peaks, and that's why our energy state, these energy states are plus 3 by 2, plus half, minus half, and minus 3 by 2. Now you can see that total 8 transitions are possible. Okay, from this plus by 2, this can move to plus 3 by 2, plus half, minus 1 by 2, and minus 3 by 2. And from this minus half, it will again have 4 possibility. But according to spin selection rule, we know that the difference of this delta I mi should not be greater than 1. That is, it should be either 0 or half. And that's why we cannot consider this transition, that is I is equal to plus half to minus 3 by 2, because minus 3 by 2 minus plus half is minus 2, and that's why the value is not 0 or 1, and that's why this transition is not allowed transition. In a similar way, this transition is also not possible, that is minus half to plus 3 by 2. It is also not possible because the delta mi in this case will be plus 2. Okay, so spin selection rule, we all know that it should be either 0 or 1. So these signals are called as allowed signal, and if the I value is mi value is not 0 or not 1, that they are forbidden transition. So only allowed transitions are going to be appear over here. And since 6 allowed transitions are probable in this case, we will be having 6 different cases. Okay, so same 57 Fe, same 57 Fe based upon its different environment. We may have one signal at 0. We may have a signal on the negative side. We may have two different signal. We may have 6 different signal. So the environment of that nuclei is going to govern the number of signal and absorption of gamma radiation. So in a one diagram, we can see that this is the isomer shift. It is a positive side over here in this case. Okay. See, this x scale over here is millimeter per second. That is velocity of that reciprocating motor, and the magnitude is millimeter per second. So this is going to show, ultimately this is going to show the energy of gamma radiation, because based upon the velocity of that motor, we will be having gamma radiation of different energy. Okay, and over here we have the count of gamma radiation. Okay, at resonating condition, since the gamma radiations are absorbed by the absorbed nuclei, we will be having a sudden dip, and that is appear in the form of a signal over here. This can be at 0, this can be at positive side, this can be on the negative side based upon isomer shift. We may have this quadrupole splitting also, and we may have this due to magnetic effect, that is ferromagnetic environment or Zeeman effect. We may have the signal splitted into 6 different signal. So this is hyperfine splitting, this is quadrupole splitting, and this is isomer shift. So in this way, we can judge the environment of any material. Okay, based by studying the 57 Fe. If 57 Fe is present, or 57 or 119 SN is present, so by studying that two 57 Fe or 119 Sn, we can know about the environment of whole material. Okay. So again, the same thing, 57 Fe, if it is present in stainless steel, which is a non-ferromagnetic cubic environment, we will be having a negative isomer shift value. Okay. And only one signal. If this FeSiO4, if we talk about this FeSiO4, then in this material also we have Fe iron, and the environment is paramagnetic or diamagnetic. So we will be having a quadrupole splitting in this case, and due to dipole interaction over here, that is when Fe is present in the iron rod, we will be having a ferromagnetic environment, which is a non-cubic environment, that is non-spherically symmetrical environment. And due to that, we will be having we will be having 6 signal due to 6 allowed transition. We will take some of the example, that is FeSO4 6H2O, potassium ferricyanide, potassium ferrocyanide, FeCO5, FeCl3. First example is FeSO4.6H2O. In FeSO4, we know that Fe is present in the Fe plus 2 state. SO4 is minus 2, Fe is plus 2. So the 3d6 4s2, and when we have Fe plus 2, 2 electrons are removed from s orbital. So this is the distribution of T2g orbital and Eg orbital. T2g orbital are dxy, yz and xz, and Eg orbital are dz square and dx square dash y square. So we can see that in this region, that is T2g region, we have 4 electron, and in the EG region we have 2 electron. Means both these orbitals are half filled. Over here, one orbital is full filled and 2 electrons are half filled. So we can say that the distribution of d electron is not spherically symmetrical, and that's why in the case of FeSO4.6H2O, we will be having 2 signal due to quadrupole splitting. Okay, see, it is not always necessary that we observe this quadrupole splitting in the terms of paramagnetic or diamagnetic environment. Again, we need to see what is the distribution of this d electron also. Okay, because d electron density is also going to affect the magnitude of effect of that s electron density. So over here we get 2 signal because of different environment of electron in Eg orbital and T2g orbital of FeSO4.6H2O. In a similar way, if we consider this FeCl3.6H2O, FeCl3, in FeCl3 we have this Fe plus 3. You can see that now 2 electrons are removed from s orbital and 1 electron is removed from this d orbital. So in T2g orbital we have 3 electron, that is all the orbitals of T2g are half filled, and all the orbitals of this Eg orbitals are also half filled. So the orbitals of T2g and Eg both are half filled. All the orbitals are half filled, and that's why we have electron density, symmetrical electron density, and that's why over here we are going to get only one signal. Okay, so in the earlier case, in the case of Fe plus 2, so we are discussing that what are the different factors that can affect the number of peak and the position of a signal in the Mossbauer spectroscopy. So this is one of the factor. So in the FeSO4 we have 2 signal. In the case of FeCl3 we have only one signal. Potassium ferrocyanide. Okay. In the earlier case, we can see that this both complexes are high spin complexes. So they are going to obey the Hund's rule. Okay. But in the case of this FeCN6, this is a low spin complex. And that's why you can see that over here, the electrons are paired. Though we have Fe over here, this is Fe is Fe plus 2. But since this is a low spin complex, it is not going to obey the Ohm's rule, and that's why all electrons are going to become into T2g orbital. So again, what will be the problem? The problem is in T2g, all the orbitals are fulfilled. EGs are empty, but all the T2g orbitals are fulfilled. Okay, and that's why again we have a spherically symmetrical charge distribution, means symmetrical charge distribution, and that's why we are going to get only one signal in the case of K4, FEC and 6. Though it is a Fe plus 2. See, in the earlier case, Fe plus 2 is having two signal over here. You can see that this is also Fe plus 2, but it is having two signal. But in this case, Fe plus 2 is having one signal. In a similar way, if we talk about potassium ferricyanide, again, this is a low spin complexes, so electrons are going to be paired. Now you can see that in the T2g orbital, the two orbitals are filled orbital and one orbital is half filled. So again, we don't have any uh, symmetrical charge distribution in the T2g orbital, and that's why again the signal of this K3 FeCN6, it is going to be splitted into two signal because we don't have spherically charged distribution of p orbital. Okay, so based upon the ligand also, what kind of ligand we have? Either we have a strong ligand or we have a weak ligand. So based upon strong ligand or weak ligand, we may have either high spin complexes or low spin complexes, and based upon that, we can judge the environment of T2g orbitals and EG orbitals, electrons present in the T2g orbital and EG orbital, and that are also going to affect the signal in the Mossbauer spectroscopy. Now let's consider the symmetrical criteria that we have. This FeCO5 pentacarbonyl iron. It is having trigonal bipyramidal geometry. Now you can see that two carbonyls are present at axial position and three carbonyls are present at the equatorial position. So the ligands, see if three carbonyls are present at the axial position and three are at the equatorial, or on both the cases we have two, then we can see that all these carbonyls are arranged symmetrically, axially and equatorially. But over here, axial carbonyl and equatorial carbonyls are different, and that's why you can see that we again will get two different signal in the case of FeCO5. Let's consider this Fe3CO12. It is a bridge compound. Carbonyls serve as the ligand of bridge ligand, and due to this complexity in structure, you can see that we will get different number of signal over here. We have two Fe over here, three different types. We have three Fe over here. This the environment of these two Fe's are same, but the environment of three Fe is different, and that's why we have complexity. We have complexity related to isomer shift. We will have complexity related to quadruple splitting, and that's why we will get four signal over here. Three signal in which one signal is splitted into doublet. So based upon the symmetry of any particular molecule or compound, we may have different observation in Mossbauer spectroscopy. Let's consider one more case, that is sodium nitroprusside, Na2FeCN5 nitrosyl. If all the ligands are cyanide or nitrile ligand, then we will be having octahedral geometry. But over here, and in that case, we may have observed only one signal in this case. But since we have one a nitrosyl ligand, NO plus ligand, it is going to overall affect the peak position and number of peaks in the Mossbauer spectroscopy, and that's why instead of one signal over here, we will get two different signal in the Mossbauer spectrum of sodium nitroprusside. So in this way, we have discussed through some of the example that this how isomer shift, how quadruple splitting, and how this magnetic moment, the environment of any atom, that is Fe or Sn or zinc or nickel, are going to affect the Mossbauer spectrum of this respective element. We have also studied the symmetric criteria of metal complex. We have also discussed the whether the complex is high spin or low spin that is going to affect this Mossbauer spectrum or not. So all these uh, factor can influence the Mossbauer spectrum of any element that is 57Fe or 19119 SN. See, why I on the whole lecture I have discussed only about 57Fe because the most of the work on Mossbauer spectroscopy have been done on 57Fe. But other element like zinc, nickel, tin can also be studied by this spectroscopy. So with this, the concluding remark is that Mossbauer spectroscopy remains the gold standard for quantitative determination of the valence state of iron in minerals and identification of various iron oxide. It is also well suited for determination of the coordination number of Fe atoms. Questions you can send me. I will be available. You can take my contact from website. It is already available over there, Sardar Patel University. I am really thankful to all of you for patiently listening me. And if you have any query regarding this Mossbauer spectroscopy, you can anytime contact me. So with this, again, I would like to thank UGC MMTTC Director Jagdish Joshi sir, and my dear friend and coordinator of this program, Dilip Vasawa sir. Thank you all.